Okay, let's have a look at what affects the magnitude of lattice enthalpies. Okay, remember they'll always be exothermic, they'll always be negative by definition. And we could have done it the other way around, but convention has it that it's the exothermic change when 1 mole of lattice forms from its constituent gaseous ions. So, what's going to make a lattice strong? Obviously the size of the ions. The structure of the compound, it's something we don't really get into too much, crystal structure, but the size of the ions is important. So if we can get the ions closer together, then obviously the electrostatic force of attraction between them is stronger. Okay, so the closer they can get together, the stronger that force. So the smaller the ions, the larger the delta H lat, keeping all other variables constant. Okay, small ions means small ionic radius, so the centers of the charge can be closer. If we increase the charge on ions, then the lattice enthalpy increases, logically. We double the charge, we double the force, so obviously we make a stronger lattice. So charge, size and charge. Sometimes we're going to have to take into consideration that the bonding might not be fully ionic. It might have some covalent character, and this affects the magnitude of the lattice enthalpy. So we'll discuss that in more detail later. Let's have a look at these tables. Now, what have we got here? Some trends. We're looking for trends. So to have any idea of what's going on, we've got to look at changing one particular variable, haven't we? So let's look, for example, at the fluorides of group 1. They've all got the same charge. What's happening to the size of the ions? They are getting bigger going down the group, so the centers of the charge are further away, so the lattice enthalpy is less exothermic. Okay, you need to write your own notes for this. You can repeat the video and just come up with some very simple trends. So that's going down group 1 fluorides, the same pattern going down the chlorides, the same pattern going down the bromides, etc. How about if we compare two anions, fluoride ion and the oxide ion are of similar sizes, with lithium fluoride, lithium oxide. What's happening here? Well, we're increasing the charge, aren't we? So if we double the charge in the oxygen on the oxide here from fluoride, then again the lattice enthalpy increases by 3-fold in this case. So charge is very important there, isn't it? Okay, and you can see that in all of the elements. Look, to go from a fluoride to an oxide, it always goes up. Look at aluminium fluoride to aluminium oxide. We could also look at the charge on the cations. So lithium fluoride, magnesium fluoride, the charge on the magnesium. Even though the magnesium ion is bigger, the charge is double and the lattice enthalpy increases. So we have to take into account both factors. And aluminium fluoride has got a massive lattice enthalpy. Aluminium ions are quite small and they've got a very big charge. Okay. I'm going to correct myself there and say I mentioned lithium ions and magnesium ions. Magnesium ions are definitely bigger, but they've got a bigger charge. We'd have to compare lithium ions with beryllium ions when we're comparing the fluorides, wouldn't we? Because the beryllium ions are more or less the same size. They're slightly smaller than the lithium ions. But even then, the big effect we see is due to the charge on the beryllium. We're taking two elements in the same period. So it's fairly clear. A couple of points to note, just so you've got these notes down definitely. Group 1 halides, the magnitude of delta H lat decreases down the table. Okay, and that makes sense, doesn't it? You can see that decrease. That's very clear, that trend. and the magnitude of delta H lat is greater for group 2 fluorides than for group 1. So group 2 fluorides, lithium and beryllium, sodium and magnesium, there's a massive increase in the lattice enthalpy. Okay, let's look at other data. Let's look at the trends here. What's happening? We're going across the period. The charge is increasing. Ionic radius is decreasing slightly, but the charge is definitely increasing. Look at the increase in the lattice enthalpies. That's really to do with increasing charge going across that period. Point to note, just to make sure you've got it down, the delta H lat is greater for group 2 oxides than for group 2 hydroxides. Oxides and hydroxides. Okay, let's have a look. Magnesium hydroxide has got 3006 kilojoules per mole, and magnesium oxide 3791. Why? Why is there a greater strength of lattice with the oxide? Well, the obvious reason is that it's got a 2- charge. Okay, these are slightly bigger too, so distance is going to come into this slightly, but there's a 2- charge there, so the lattice is stronger. Let's have a look at this. This is going across the period, sodium, magnesium, aluminium. It's period 3, isn't it? And the fluorides, obviously, the lattice enthalpy increases. We've seen that from the previous table, but just to drive home the point. A couple of extra notes here. Distance between the ions depends on the crystal structure. We don't really talk about this at A level anymore, but there are different ways of arranging ions within a crystal structure, and that will affect how close they can get together. Okay? We don't really take that into account. And whenever we've got any kind of chemical bonding going on, we're looking for more stability, aren't we? A lower energy. So here you can see these massive enthalpy changes. They're exothermic processes, aren't they? And you can see the massive stability that is created when we put together a crystal lattice from ions. And that's very important in the formation of ionic substances. They're producing a much lower energy state, aren't they, by forming solids. Okay, what do lattice enthalpies do? What effects do they have? Well, if you've got a very high lattice enthalpy, you've got a very high melting point. So magnesium oxide had a massive lattice enthalpy, and it's used for lining furnaces because it won't melt until, I think it's about 3000 degrees. Okay. The solubility of the ionic compound will depend on the lattice enthalpy, but also on hydration enthalpies. And we'll discuss that more later. So we've got to break down the lattice. Somehow we've got to get that money back from the energy bank. And we'll talk about hydration enthalpies in a little while. This is important now. This is like a tertiary factor when you talk about the strength of lattice enthalpies, but it's an important detail. If we use Coulomb's law, which is purely theoretical, we can work out the lattice enthalpy for a given ionic substance. But we used our Born-Haber cycle to work out the actual experimental lattice enthalpy. And we find that there's a difference between the calculated lattice enthalpies and the experimental lattice enthalpy from a Born-Haber cycle. When there's a significant difference, we can explain that using something called covalent character. So the degree of covalent bonding in the substance can affect the lattice enthalpy. Okay, well, how does this happen? If you look at these substances here, going across period 3, we've got sodium chloride, magnesium chloride, aluminium chloride. We've talked about this already, that the aluminium's got a much bigger charge, so that charge on the cation can distort the electron cloud on the chloride ion, as shown. Okay? So here what happens is the electron clouds get progressively closer to the cation. Electrons being closer, we could say that they start to almost share the electrons, and we've talked about aluminium chloride being covalent before. But what happens to the center of the charges, the positive and negative charges, is that they come closer together. So the bonding becomes stronger. Okay, this is called polarization. The centers of the positive and negative charges are closer together, the force of attraction is greater, and the lattice enthalpy will be slightly more exothermic. Okay. It's also important to take into account, and we'll look at it on the next page, the size of the anion. It's very hard to polarize a fluoride ion, but it's very easy to polarize a bromide ion because it's much bigger. It's got many more electrons. Those electrons are much farther from the nucleus, so it's easier to polarize. We say that the anion is more polarizable. So aluminium, of these three cations, the aluminium is the most polarizing, and of these three anions, the bromide is the most polarizable. Okay? We just talked about this. So the more the polarization, the greater covalent character, and the difference between the experimental lattice enthalpy and the theoretical lattice enthalpy is greater. Okay, more polarization, more difference between the two figures. So that's the first rule we're going to look at. Small, highly charged cations with a large charge density have more polarizing power and cause more covalent character. Okay, there it is again. So let's look at that on this table. What have we got? We've got the chlorides going down group 1, haven't we? Sodium, potassium, rubidium, and cesium. Okay. And we've got the lattice enthalpy from the Born-Haber cycles. And we've got the theoretical lattice enthalpy. Yeah. So this is the real figure and this is the calculated figure. Now the difference between these figures here is relatively small, isn't it? You can see. If we look at the chlorides going down group 2, we've got the Born-Haber cycle, the true figure, and we've got the theoretical figure. And you will see that there's a big difference higher up the group. Going down the group, the difference decreases between the numbers. We have to somehow explain that. So the rule is highly charged cations, Mg2+, Ca2+, Sr2+, they can cause more polarization. Okay, great. So going down group 1, it's quite a small charge on the cation, so it doesn't cause a lot of polarization, so there's not a big difference between the figures. But when we've got a small, highly charged cation like magnesium, it does cause a big difference between the numbers. Okay? So these chlorides here, we can say that they're almost completely ionic, whereas magnesium chloride and calcium chloride, to a lesser extent, have got more covalent character. Okay. The magnesium 2+ has more polarizing power because it's got a high charge density, and so it deviates more from the pure ionic bonding. The lattice enthalpy is more exothermic. There's a stronger lattice. Rule 2, the second rule we're going to apply, is that anions that are big and have got lots of electrons are more polarizable. Okay, so if we've got a more polarizable anion, we're going to get more covalent character. Let's have a look at this. So as we go down, sodium magnesium, fluoride, iodide. Obviously, the fluoride ion is much smaller and has many fewer electrons than the iodide ion. Okay, so we'd expect the iodide ion, large with lots of electrons, to be more polarizable. Okay, so with the fluoride, sodium fluoride, then the difference between those two figures, the experimental and theoretical, is fairly small, isn't it? But with the iodide, it's bigger. You can see there's a logical jump because the iodide is more polarizable. Although the sodium ion, the cation, hasn't really got a lot of polarizing power, you can still see a trend that you would expect. If we take magnesium fluoride, okay, magnesium's more polarizing, so there is some covalent character, isn't there? This is more exothermic than this, so there is some covalent character in the compound. But if we look at the covalent character of magnesium iodide, there's a massive difference. This has got a significant covalent character, magnesium iodide, because the magnesium with its large polarizing power and the iodide with its polarizability, it's polarizable, it causes a significant degree of covalent character. So the difference is much bigger. Okay, it's a lot to take in. Take your time, have a look at the pages indicated and do the questions associated with this work.